This is the second part to our video set on properties of limits. The next one that we're going to discuss is the limit of a product rule. The limit as x approaches a of f of x times g of x is the limit as x approaches a of f of x times the limit as x approaches a of g of x. That is, the limit of a product is the product of the limits. But once again, just like our sum and difference rule, we're basically just applying that limit to each factor or function in the larger limit. So there's another one, our constant multiple rule. This is not in our pre-calculus book, but it is in every single calc book, so I think it's appropriate for us to talk about it now. It says that the limit as x approaches a of a constant times a function is that constant times the limit of the function. So basically just here comes out in front. This really just comes from an application of our product rule. See, the product rule above says that this would split up into the limit as x approaches a of c times the limit as x approaches a of our function f of x, and we know that the limit of a constant is just that constant. So this right here turns into just c, and that's where we get the right-hand side of this rule. We also have the limit of a power rule. So if you have the limit as x approaches a of some function f of x raised to a power, so that power is like on the inside of the limit. Oh, that's the same as just taking the limit as x approaches a of the function and then taking that answer and raising it to the nth power. Because all radicals can be rewritten as rational exponents, this extends to radicals. The limit as x approaches a of the nth root of f of x is equal to the nth root of the limit as x approaches a of f of x. So we can just find the limit of the function and then take the nth root of that. Let's suppose that the limit as x approaches 4 of f of x is 10, and the limit as x approaches 4 of g of x is equal to -3. We want to start by finding the limit as x approaches 4 of x times f of x. Here we're going to use our product rule. This becomes the limit as x approaches 4 of x times the limit as x approaches 4 of f of x. Now I know it's a pain to write this limit as x approaches whatever over and over and over again, but you have to. You absolutely have to. The limit as x approaches 4 of x using our identity function rule. This here becomes 4 times, now the limit as x approaches 4 of f of x was given above. That's 10. We get 4 times 10. Our limit is 40. In part B, we want to find the limit as x approaches 4 of g of x squared. Well, that's the same as the limit as x approaches 4 of g of x, finding that, and then squaring it. The limit as x approaches 4 of g of x was given to us. That's -3. So this becomes -3 squared. Our limit is equal to 9. In part C, we want to find the limit as x approaches 4 of the square root of f of x. Our limit rule for radicals tells us this is the same as the limit as x approaches 4 of f of x, and then take the square root of that result. The limit as x approaches 4 of f of x was given to us. It's equal to 10. So we get the square root of 10. That can't be simplified. There's our answer. In part D, we want to find the limit as x approaches 4 of negative 9 times g of x. We saw that the negative 9 comes in front of the limit. So we have negative 9 times the limit as x approaches 4 of g of x. The limit as x approaches 4 of g of x was given to us. So we have this negative 9 times out in front, and then the limit as x approaches 4 of g of x was equal to negative 3. Our limit becomes positive 27. Our next rule is the limit of a monomial rule. We're kind of combining our constant multiple rule and our identity function rule and our power function rule here all into one. Once we get the basics down, we're able to do some combining that makes life a whole lot easier. The limit as x approaches a of b sub n times x to the n is equal to b sub n times a to the n. Now that b to the n there, that's just a coefficient. The only reason that it has a subscript on it is because when we have a polynomial, because eventually we're going to expand this polynomials, and we know a polynomial is a bunch of monomials added or subtracted together. The only reason that that subscript of n is on the b is just to differentiate between the different coefficients that we're going to have once we have a big polynomial instead of a single term. Basically, all that's happening is the constant stays the same, and that's kind of our constant multiple rule where that constant comes out in front. So that's what's happening here. Then, here, maybe let me write it out like this. So the limit as x approaches a of b sub n times x to the n. This becomes, right, b to the n out in front, and then we have the limit as x approaches a of our x to the n. Well, then we saw that with our power rule, that b to the n still out in front, this becomes the limit as x approaches a of x, and then all that raised to the n. What I have in my brackets there, that's our identity function rule. The limit as x approaches a of x is just a. So there's our b sub n out in front, and now this becomes a, and then we're raising it to the nth power. So that's what's happening. But long story short, just take the a and plug it in for the x, and that's it. We want to find the limit as x approaches negative 2 of 5x squared. All we need to do is take this negative 2 and plug it in for the x and clean it up. Since I'm actually plugging a number in for x, I can drop that limit notation. We only write the limit as x approaches negative 2 until we plug a number in. So this is going to become 5 times negative 2 squared. That's 5 times 4. Our limit is equal to 20. All right, one more rule for us, and this is the limit of a quotient rule. The limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f of x divided by the limit as x approaches a of g of x. Again, we're basically just like distributing this limit thing into everything inside of our parentheses. Now, since we're dividing, we always have to be concerned about dividing by 0. So we need to make sure that the limit as x approaches a of our denominator function, g of x in this case, is not equal to 0. So we can say that the limit of a quotient is the quotient of the limits provided that the denominator's limit is not equal to 0. All right, let's use our rule. This is going to become the limit of the numerator over the limit of the denominator. When I get a bunch of terms, I like to end up putting it in parentheses. Great. Now we're going to use our sum and difference rules. Our numerator becomes the limit as x approaches -2 of x to the third plus the limit as x approaches -2 of 2x squared minus the limit as x approaches 2 of -1. And then we'll do a similar thing in the denominator, the limit as x approaches -2 of 5 minus the limit as x approaches -2 of 3x. We'll find the 5 individual limits and then put it all together. Well, for these three, we're going to be using our limit of a monomial rule, where we're just substituting our a value of -2 in for x. And since I'm plugging in, here's where I drop my limit notation. So this is going to be -2 to the third plus 2 times -2 squared. I'll get back to that last one in the numerator in a minute. And then in the denominator, right, this is going to be minus 3 times -2. And then these other two here, it's the limit of a constant. We know the limit of a constant is just that constant. Oh, look, I made a mistake here. Look, I double counted the negative. Careful there. It's easy to make that mistake. Since I have the negative in front of the limit, I don't want to have it in front of the number. All right, so the limit as x approaches -2 of 1 is 1, and then the limit as x approaches -2 of 5 is 5. And I would just need to clean all this up. That's going to be -8. It's going to be 4 times 2 plus 8 minus 1 over 5 plus 6. We get -1 over 11. In the next video, we'll really start putting all of these rules together. We're going to learn an important couple theorems and find limits algebraically.